Hi everyone and welcome to another video. So today we're going to be learning about the factor formula in trigonometry. So this one is going to be a little bit complex, but I'm going to explain it to you from the very core, and I'm sure you will have a firm understanding of the factor formula by the end of this video. So just stick along, get your cup of coffee and your notebook, then let's learn something new. Alright, let's get into today's video. Okay, so today we move on to factor formula, and this is going to be another important concept. So what is a factor formula? And then what does it mean to factorize? To factorize means to express in the form of a product. The set of identities called the factor formula convert expressions such as cos A plus cos B, cos A minus cos B, sin A plus sin B, or sin A minus sin B into a product, and hence factorizing the expression. So what you may not know is so far we've been doing numbers that actually have the same angles. For example, we've been doing numbers where there is cos theta plus sin theta, and where we have, it's like, for example, A here and A here. So we've never done numbers where the angles are actually different and where we actually have cos. So we have this cos with a different angle, with a cos of a different angle, or a sine of a different angle and a sine of a different angle. So now when it comes to this, that's where factor formula becomes important. So we're going to learn how the factor formula works. So this is going to be a little bit complex, but I'm sure that since you've turned into the video, you will actually have a perfect understanding of it. So just pay attention. So let's derive the factor formula. So how does the factor formula come in? So let's first revise some things we've actually proved before. So we've proved the following. We have proven that cos A plus B is cos A cos B minus sin A sin B. Remember that? And then we've also proven that cos A minus B is the same as cos A cos B plus sin A sin B. Now the reason I'm using this is because if you look at this, A plus B is going to give you a different answer from A minus B. So this is actually a good illustration to illustrate two different values or trigonometric equations adding themselves that actually have different angles. So this can actually work for us. So we can actually test it like this. So if we choose to add this and this, so it's going to help us derive some formula. So if we choose to add cos A plus B and then cos A minus B like that, remember that this case works perfectly because this angle is obviously different. The answer here is obviously different from the answer here. So this will be a perfect use case. Alright, so remember when we expand this, this becomes that, and then this becomes that. So we actually have this. Then when we expand it like that, we can actually see that some of these values cancel. So this cancels with, actually, this cancels with that. Then we remain with this plus that, which gives us 2 cos A cos B. So this is actually what comes out when you add cos and cos. So thus we've derived this equation. I hope that makes sense. So let's see, what if we chose to subtract the two different values? We would have this and that, but then the difference here is this and this will cancel, and then we'll end up with negative 2 sin A sin B. As simple as that. So that becomes another formula for factor formula when we actually have cos subtracting. So you're gonna see, and this will make sense. Alright, so we've also proven that sin A plus B is equal to that, and then that sin A minus B is equal to that. So let's see what happens when we choose to add. So if we add the two, we actually have that, then we'll have this happening, then we'll actually have this and this will cancel, then we'll remain with 2 sin A cos B. That's we derived another important formula. Alright, so let's see what happens if we choose to subtract. If we choose to subtract, we have that. Then you can actually see that sin A cos B again cancel. Then we now have 2 cos A sin B. That's we derived another formula. Alright, now we're going to proceed to the other step of factorizing a sum or difference of two cosines. So this is it in summary. So this is what we derived in summary. So this is what we've just derived. Alright, so for convenience purposes, we're going to simplify this. So instead of writing it this way, because this is so bulky, instead of writing it this way, we're going to simplify it for convenience purposes. So what we shall do is we're going to let P to be A plus B, and we're going to let Q to be A minus B. So P is going to represent A plus B, and Q is going to represent A minus B. Alright, so what happens if we add P and Q? So remember right now, P is equal to A plus B and Q is A minus B. So if we add the two, we have P plus Q, which is going to be equal to A plus B plus A minus B. So the B's will cancel and remain with 2A. So P plus Q is now equal to 2A, of which if we make A the subject, A becomes P plus Q over 2. Now this is important because now we can actually substitute something right. So right inside here, wherever there is A, we're going to have it being represented as P plus Q over 2 because we've changed those into P and Q for convenience purposes. So what if we subtract P minus Q? So we have A plus B minus A plus B. So the A's cancel and remain with the B's adding themselves, which will give us 2B. Then when we make 2B the subject, we have P minus Q over 2. So when you substitute this, when you substitute the value of A and the value of B into the four identities, we have this. So cos P plus cos Q is going to be 2 cos P plus Q over 2 cos P minus Q over 2. Then we're going to have cos P minus Q being equal to that. Then we're going to have sin P plus sin Q being equal to that. And finally, the fourth identity is going to be sin P minus sin Q is equal to 2 cos P plus Q over 2 sin P minus Q over 2. Alright, so these are the four identities that we're going to be making use of whenever we work with factor formula. So in summary, these are the ones that you actually have to memorize. So once you memorize this, I promise you everything will be much easy from here. Alright, so now we're going to look at the reverse form of factor formula. So now there are cases where we actually need to use the reverse form. Now these reverse formats that I'm going to show you cannot easily be derived, but they just have to just be memorized. But by memorizing them, they're actually not complicated. It will help you understand the difference. So in this other case before, we've actually seen that we can express this into that. Now we're going to be looking at cases where we actually work in the reverse. So what if you're given a value that already has cos P and cos Q and you're asked to express it in reverse format? What I mean by reverse format is that you actually have to introduce a plus sign to the middle so that they actually have two different elements adding themselves. So cos P cos Q can be expressed as a half this plus that, okay? And then sin P sin Q can be represented as negative of that. Then sin P cos Q is going to be represented as that. And then that's how we represent cos P sin Q. So basically, in summary, when it comes to factor formula, as long as you have a basic memorization of those four identities that we had derived, and then you also memorize these basic reverse formulas of factor formula, you'll actually have a better understanding of factor formula. Now, to make this memorization here easy, you'll actually see that this is actually quite similar to what we've actually been doing before. So this is just a reverse. Like for example, when you look here where we have the cos P and cos Q, when you see cos P and cos Q adding themselves, and you can see that there is a similarity, that here it's cos. When you see cos P minus cos Q, you can actually see that here it's negative to sin. So the similarity here is that so you can see it here again, when cos of something different is adding cos of something different, you can actually see that there is a cos here. But now the different thing is, instead of having the 2 being this side, we actually divided both sides by 2, and the 2 is actually on the right hand side. So this is quite similar to the other. So it's more of a reverse way of stating it. So the same thing happens with this. So this is the reverse way of stating it. And remember, there was a negative 2 in front of this that actually just changed. So we divided both sides by negative 2, and we actually have a negative a half this side. So this is just basically a reverse. So that's it. So this can not only be derived but not proved. So now that we've had a grip or an introduction to all these 8 different identities, the 4 factor formula identities, and then this reverse of factor formula, I feel now we are ready to attempt some numbers. All right, let's try something. So we have this question: solve the equation sin 3x plus sin x is equal to 0 and the corresponding values of x from negative 180 to 180 degrees inclusive. So this is our equation here. So we actually have sin 3x plus sin x is equal to 0. So by looking at this, basically you can already see that this is actually an example of a factor formula. So aside from all the numbers we've been doing before, in this example we have sin. So we have sine on both sides. So that's one of the ways you know that it's factor formula. And you can actually see that the angle here is different from the angle here. So that's a clear sign that this is a number that needs factor formula. So this is 3x and this is x. So this clearly needs factor formula. So when we look at our factor formulas here, we can actually see that where we had a sign, adding a sign, that we actually have to express it in this format. So a sign of p plus sign of q is expressed as 2 sine p plus q over 2 cos p minus q over 2. So what this means is we convert this and express it into this product format. So we're going to add the value of p and q. So p and q will add, then we'll divide the answer by 2, and then in the cos side we'll have p subtracting q over 2 and putting that value on the other side. So let's go back to our example. So what happens here is, in this case, we're going to express it in the other format, but then, so we're going to use sine p plus sine q because this is what it represents. It's exactly that. So we're going to have, so when you add 3 plus x, 3x plus x is 4x, and then 4x divided by 2 is 2x. Do you see the similarity? And then when we have 3x minus x, the answer is 2x. 2x divided by 2 becomes x. That is because we have p minus q here over 2, which is 3x minus x, which is equal to 2x over 2. And that's how we have it like this. So this is how it's stated in a product format. So now that we have it like this, it's now going to be simpler to work with. As you can see through this equation, it's already clear that we can either say 2 sine 2x is equal to 0 or cos x is equal to 0, because these are just two values multiplying themselves. So each one of them can actually equate to 0. So when we work with, so when 2 is sine 2x is equal to 0, let's first deal with this. So we can actually see that we can actually divide 2 on both sides. 0 divided by 2 is 0. So remain with this. So sine inverse of a 0, so when you press in our calculator, because I want you to do this for your memorization. Sine inverse of a 0 is 0. Okay, so what does that mean? So now we've drawn our cast diagram right here, and then we're going to place a 0, and remember this is a positive, so we're going to place it in regions. So the value we get, which is 0, we're going to place it in regions where sine is positive. So that is this region and this region, CAST. So we're going to place a 0 in this region. So we have a 0. So 0 will just basically be on this line. Then we also have a 0 on this line. So what that means is for our revolution, so our first revolution, the first value will be 0. Then our second one will be that. But I want you to pay attention to something. Remember that when we find the final value of x, we're going to find it after dividing both sides by 2. So that means we can actually look for an even bigger value. Though we've been told that the range is negative 180 to 180, we can actually even get a bigger value because we're going to divide the answer by 2. So I believe getting the next one, which is 360 degrees, will still work, because 360 divided by 2 is 180, which still fits in this range. But now I think we can no longer go beyond that, because I think 360 is the highest value that can give us a 180 degrees when it's divided by 2. But now in this case, we're also allowed to have negative values, so we can actually do some clockwise revolutions. So in the clockwise direction, of course, the first value is still 0, of which we already found that out, and then our next value shall be that. So we have the negative 180, and then I believe we can also do the next revolution. We can actually move all the way here. So that's moving to negative 360. The reason we've gone up to negative 360 is because also not when you also divide that by 2, by this 2, to get the real value of x, that also still fits in the range, because 360 divided by 2 is negative 180. So that also fits for us. So these are the values we've actually derived. So we have the negative, so 2x is equal to negative 360, negative 180, 0, 180, and 360 degrees. So dividing everything by 2 to find the real value of x, we have that. And thus we found our values of x. All right, let's move to the next question. Oh, there's actually another part to this. So how about when cos x is equal to 0? Remember that cos inverse of 0 is 90 degrees. So what does that mean? We're going to put a 90 degrees in regions where cos is positive. Cos is positive here and here in the first and fourth quadrant. So our 90 is going to revolve up to here. So that means our 90 is on this line here, and then we also have the 90 on this line. Sorry, it's not straight enough, but that's basically an illustration. So when we do the first revolution, we actually have this. Okay, so our first one is 90. I think we can also get the second value, which is 270. Oh, actually, in this case, we're not dividing anything by 2, so we're actually getting real values of x. So that means this 270 will actually not work. So we actually are only going to consider the 90. So in the negative direction, we shall also only consider this, because we're not going to divide anything by 2. So we have the values positive 90 and negative 90. All right, so I've actually seen that. Because actually we're getting the real values of x itself directly. So you have x being equal to negative 90 and that. So therefore the roots of the equation between negative 180 to 180 are this. Alright, as simple as that. Alright, let's move on to the next question. So question number 2 is a little bit different. Now this actually has 3 different elements in our trigonometric equation. So being told solve the equation, this, and the corresponding values of x from 0 to 180 degrees. So pay attention to the limits. Now, this is also a factor formula. How do I know that? So everything is in terms of cos, and you can actually see that the angles are different. So you have 6x here, 4x here, and 2x there. So now when it comes to such a number, what we do is, since there is no formula that actually does three of them at once, we shall actually deal with a pair at a time. But now we actually have to be careful with the values that we pick. We have to make sure that it's actually a value that will rhyme. What happens is, if we pick this value here, if we choose to first combine the 6x and the 4x, we will not be able to solve this equation. Do you know why? It's because a 6x plus a 4x is 10x, and when you divide that by 2, we get 5x. And then what happens is, if we solve it in that pattern, we will not be able to solve the equation. So we have to solve this equation in a way where it is possible to pull something out of the bracket. So what I've seen is, when I look at this, is it's wise to group this and this first, because 6x plus 2x is 8x, and then 8x divided by 2 is what? 4x. So if we deal with this pair, this one and this one together first, we'll actually have a value that can pair along with this, and we'll have something to pull out of the bracket. So it's wiser to solve this. So when you're given an example that has 3 pairs, always pay attention to that. So choose the grouping wisely. All right, so in this example we have that. So we're going to choose, so definitely we're dealing with cos p plus cos q, because everything is cos values adding. But we're going to first group the cos 6x with the cos 2x. That's why we brought it closer to the cos 2x. So what happens when I apply factor formula on this? So applying factor formula here, so we actually end up with 2 cos 4x cos 2x here. It's because of the expression, because that's how the cos values add. So p plus q, which is 6x plus 2x, is 8x, divided by 2 is 4x. So 6x minus 2x is 4x, divided by 2, it's 2x. So that's how we end up with that. Alright, so let's proceed with that. As you can see that now that we've chosen wisely, we can actually easily factorize out something out of brackets. So we can pull out the cos 4x, and then we end up with that. Now we can see that this is equal to 0, or that is equal to 0. Now let's first deal with the cos 4x is equal to 0. Now we know that cos inverse of 0 is 90. Okay, so we're going to place that 90 in regions where cos is positive. So we have this, and we have that. Now this is a unique case, because the final answer we're going to get the real value of x, we're going to be dividing it by 4. Now this means we can do quite a number of revolutions, because we actually have a big range. But remember, we're not out to go beyond 180. So whatever value we get, we shall compare and see if we divide it by 4, is the answer still in the range? Right, let's see. So in our first revolution, because here we're not doing any negative resolutions, because it's 0 to 180. So we have 90 degrees, which fits in the revolution, obviously. Then we have 270, but remember the 270 is going to divide 4. It's going to be divided by 4 at the end of it, and of which that is 67.5, so that fits in the range. But I think we can actually go even further. So let's see, what about the next value? So the next value is 360 plus 90, which I believe totals to, I think totals to 450. So when you get 450 divided by 4, the answer is 112.5, and that is still in the range. So what if we try another revolution? So we now have this, it goes past 360 again, then it goes to that. I believe this value can be gotten by doing 360 plus 270, which is equal to 630. When you divide that by 4, it actually still fits in range. So we actually also have the 157.5, because 630 divided by 4 is 157.5. Now, how about the next one? Let's see, 630 plus 180 will be, so I'm pressing it on my calc, plus 180 is going to be 810. 810 divided by 4 is 22.5. So I believe that is how far we need to go. So we'll end on that. So these are the values we've gotten. We've actually gotten 90 degrees, 270, 450, and 630. So when you divide everything by 4, we actually have that. So those are the values of x. Alright, how about when 1 plus 2 cos 2x is equal to 0? We can actually take the 1 to the other side, then we have a negative 1. Then we divide both sides by 2, then we end up with that. Alright, so cos inverse over half we know is 60, and we're going to place the 60 in regions where cos is negative because of this negative sign. So that means we're going to place the 60 in the third, and in the second and in the third quadrant. So we actually have it as that. Right, so now we're going to do some revolutions. So our first revolution is going to be that. So we're going to limit it to the positive, so that's what we have. Then we also have this. The reason I can slightly go beyond 180 is because I won't be dividing the final answer by 2. So I believe that's the farthest we can go, and where we'll have an answer below 180 degrees. So we have that. So we have 120 degrees and 240 degrees. So x is going to be 60 degrees and 120 degrees. So the answer is get after dividing both by 2. So therefore the roots of the equation from 0 to 180 degrees are that. And those will be our answers. Alright, let's go to question number 3. So question number 3 is slightly different. We have this and that. So this is actually still a factor formula number, because we actually have a cos here and a cos here, and then you can actually see that the values in the brackets are actually different. We have x plus 20 here and x plus 80 here. So this is actually a factor formula number being equal to 0.5. So how do we do this? So we're going to consider these as different values, but now we're going to apply the formula of cos. So as usual in this example, we're also going to follow the factor formula. So this is right. So this is going to be cos minus cos. So we're going to follow the cos minus cos formula. So it's going to be, we're going to use the formula of cos p minus cos q. So as you can see, if this is p and if this is q, we have x plus 20 plus x plus 80, and all the total of that divided by 2 will actually have 2x plus 100 over 2, which ends up being x plus 50 degrees. And then on this other side, we can also see that x plus 20 minus x minus 20, because of the negative sign, we can actually see that we actually have a negative 30 degrees after dividing everything by 2, because 20 minus 80 is 60, negative 60, and negative 60 divided by 2 is negative 30. So this is what we end up with after applying the factor formula. But we can actually see that this value, so for the sign of negative 30, we can actually get a direct answer, because sign of negative 30 is clearly a half. It's actually clearly negative a half. Okay, so sign of that is negative a half. Then when we multiply negative a half times negative 2, this value will multiply the negative 2. Negative a half, which you get from here, times negative 2 is positive 1. So these 2's cancel and we remain with that. All right, so this becomes that. So sine inverse of a half is going to be equal to 30. Okay, so we're going to place the 30 in regions where sine is positive. That is this region and this region. So we have that. So we're going to do some revolutions. All right, but in this case, we shall be subtracting the final answer. We're going to subtract a 50 from the final answer to get the value of x. So we can actually do this first one. So we have this. Remember, the range is 0 to 360, so it's okay to go slightly beyond. So we have that in range. Then I believe we can also consider this one. Now the third value will be 390, but when we subtract a 50 from 390, we can actually see that the answer is also in range. So we're going to take these three answers, the 30 degrees, the 150 degrees, and the 390 degrees. So to get the values of x, we subtract by 50 on all, then we end up with that. So what happens here is when you subtract a 50 from 30, you actually get a negative 20, and negative 20 is not inclusive in this range. So we're going to discard that answer. So we only keep the answer we get from 150 and that, which ends up being 100 and 340. All right, let's go to question number 4. So question number 4 is slightly similar, but now this is different from the other factor formula numbers. So this is an example of a number that requires the reverse factor formula. As you can see, we have values already stated for us in product form. So when you get a number and it's already expressed in product form, now there we apply the reverse factor formula. So this requires us to use factor formula but in reverse, and the corresponding values of x from 0 to 150 degrees. Okay. All right, now this is an example where we have sine cos. You can already see that the angles here are different. So what do we do for sine cos? Let's look at our reverse factor formula. All right, so when it comes to sine cos, we can actually see that we're actually going to be making of use. So this is how our reverse factor formula is stated. So we have it in this format. So this can be expressed as that, okay, as a half sine. So we're going to have this p adding the q, and then we're going to have the p subtracting the q. All right, this is our equation here. So in reverse factor formula, this can be stated as this. So remember, this becomes a sine, of which this is, we're going to have this as p and this as q. So p plus q is this. So we'll have x plus 15 plus x minus 15, of which you get the answer. The 15s will cancel, then we'll have x plus s, which is 2x, plus we're going to have x plus 15 minus x minus 15, of which you get an answer of 30 degrees, of which we now know that sine 30 is what? A half. Now this 2 here cross multiplies and it will multiply this 0.5 and we'll have a 2 on that side. So this is what you end up with. So we have this being equal to that. But now remember, we can take this a half to the other side, of which 1 minus a half is what? A half. So you have another positive a half, not negative a half. So we actually end up with something like that. So now sine inverse of a half is 30 degrees. So remember, with 2x being equal to sine inverse of a half. Now drawing our cast diagram, we're going to place 30 degrees in regions where regions where sine is positive, and that is in the first and in the second quadrant. So we actually have a diagram like that. But remember, we're going to be dividing the final answer by 2, so you can actually go a little bit more. So because we're going to be dividing the final answer by 2, so we're going to have our first answer as that, and we can also have that, of which this value is 150. So 150 fits because we're going to divide that by 2. So we also have, this is 390. 390 divided by 2 will also fit in range, so we can actually consider that. Then we also have, is our fourth revolution. I believe this will also fit properly, but I think that's the farthest we can go. We can only do 4 revolutions for this case. So we have 30, 150, 390, and 510. Now we can divide all answers by 2, where we'll end up with that, and those will be our final values of x. All right, let's get to number 5. So question number 5 is from UNEB 2007, and this is question number 12b. So we've been asked to solve the equation sine x minus sine 4x is equal to sine 2x minus sine 3x, and the corresponding values of x from negative 180 to 180 degrees inclusive. write this out. So now we have this number here, but now when I look at this, I see it would be wise to bring this and this together, because by doing that we'll actually have a value that can easily pull out. Okay, so let's rearrange it and have something like that. So when you apply factor formula on both of the two sides, we actually come up with this being equal to that. And to show you that this was actually the right decision to make is you can see that there is something in common. So having something in common means there's something that will pull out. So that's how you know you've made a wise decision. So we're going to bring this to this other side of the equal sign to leave a 0 on the right hand side. Then we have that. So we're going to pull cos x. We're going to factorize 2 cos x out of brackets. Then we remain with that. But now for this question, you can actually see that we need to apply factor formula again. So we're going to apply factor formula to this side again. So we end up having something like that. So now we end up having 2 cos x is either is equal to 0, or this can also be equal to 0, or this can also be equal to 0. So now let's look at the situation. When 2 cos x is equal to 0, we have that. So we have that is equal to 0, and then cos inverse of 0 is 90, and then we're going to place the 90 in regions where cos is positive, and that is this region and this region. But remember, our limits allow us to go to negative, so we actually have this value here. So we have 90. Now we cannot go beyond that, but we also have this. So we have positive and negative 90 as the values of x. So let's go for the other case. When 2 cos 5x over 2 is equal to 0, we know that cos inverse of 0 is 90. Then we also end up with something like that. But also remember in this case that we're going to also have a final answer where we divide by 5x. That means we are free to have many revolutions, because we're going to be dividing by 5. Okay, so we actually have this one, we have this. I believe we can also go beyond that. I believe we can also do it the 4th time. Now I may not be able to show everything on the diagram, but as you see that when you solve and do both positive and negative revolutions in a way like that, you end up having these different values. So you can actually go as far as 810 in the anti-clockwise rotation, and you can also go as far as negative 810 in the clockwise rotation. So these are the values that you get. Now each of these values will be multiplied by 2 and divided by 5. So we end up with something like that. So this becomes our answers. Alright, so when we go to sine x over 2 is equal to 0 for this use case, we have that sine inverse of 0 is 0. So we have a 0 on our diagram. So we have a 0 right here. So it's the region where sine is positive, this region and that region. So our first value is 0. Then we also have that. But remember, we've been told that the final answer shall be multiplied by 2 to get x. So that actually means we shall only consider the 0. Now also in the negatives, we can't consider the negative 180 that we actually get, because the final answer will be multiplied by 2, of which this is the only one that gives us an answer that is in the range of negative 180 to positive 180. So 2 times 0 is 0. So we do not consider the answer here, because this answer is beyond 180, because 2 times 180 is 360, and that is already beyond the range that we've been given. So we end up with the roots of the equation being this. Alright, let's move on to the next question. So this other question comes from UNEB 2014, and this was question number 3. So we're being asked to prove this. We are being asked to prove that cos 2a minus cos 2b is equal to negative p, and sin 2a minus sin 2b is equal to q. Prove that this is equal, that sec a plus b is equal to that. Alright, so the first step we're going to take to prove this is we're going to have to first simplify these equations. So we have this being equal to negative p and this being equal to q, but they're actually complex. So what we're going to do is we're going to find a way of simplifying both of them. So the first step we're going to do, is let's first deal with this one. So we're going to apply factor formula here. So applying factor formula, we can actually see that it expands to that. Okay, because we have 2a, we have negative 2 sine, because if we add this and this, 2a plus 2b is, so add this and this, we have 2a plus 2b over 2, which ends up being a plus b. Then 2a minus 2b over 2 ends up being a minus b. Alright, so we have that for negative p. So we can actually see that the negative signs cancel and we have that. So when you also simplify the q being that, so when you expand it becomes this. So applying factor formula, we end up with something like that. So to simplify this a little bit further, is we're going to see how to, so we're going to divide this by that. The reason we do that is we can actually see that this has a sign value. This has a sign value here that when divided by this will help us come up with a tan, and at the same time this value and this one will cancel. So that will help us simplify that value. So this becomes a wise decision to divide p by q. So when you do that, we end up with 2 sine a plus b over 2 cos a plus b. So we'll have p plus q being tan a plus b. Alright, now if we remember our the different identities that we derived at the beginning of trigonometry, remember that 1 plus tan squared theta is equal to sec squared theta. So that means there's a relationship between a tan and a sec. So we're going to make use of that relationship. So for that relationship to work first, we're going to, since in that equation we actually have the sec being squared, we're going to first square this sec. So if we square it, so let's first solve it from the left hand side. So when we square it, we actually have it being like that. So this value here is the same as root of sec squared, because if we root sec squared, it gives us this answer. So the root of sec squared, so when you find the square root of sec squared and this 2 cancels with their half here, it will give you this again. So this is actually quite similar to that. Now this can now be changed into 1 plus tan squared a plus b. So we end up having something like that. But we remember that this represents that. So remember that tan a plus b means p over q, of which, since this is squared, it means we have p squared over q squared. Now we're going to open these brackets and then we'll have the p and q being squared. Then when we find the LCM, we end up with that. And then you can actually see that you can actually pull the q out of brackets. So the q will move out of the root and we'll have it being 1 over q. So we end up with something like that. So thus we've actually been able to prove the equation. Alright, so question number 7 is from UNEB 2002 and it was question number 12a. So we're being asked to show that this becomes that. So this is an example of a factor formula proof, an identity that requires us to use factor formula. So what you can see is, in this case, we also have to be wise concerning what values we actually combine together. As you can see, it would be wise to combine the sine a with the sine 7a to give us a value of 8a over 2, which will be divided, and it will have a 4a somewhere, which will easily work with that. So it would be wise to combine and rearrange that. So from the left hand side, we actually have this. So we're going to combine the sine a with the sine 7a, and then when we work that out with factor formula, we actually see that we come up with that. Okay, but now remember that in this case, when we have a minus 7 sine a, the reason we have a negative 3a here is because negative a minus 7a is negative 6a, and negative 6a divided by 2 is negative 3a. So that's why we have a negative here and there. But now when it comes to cos, when you have a negative sign in a cos, it's actually, the negative sign actually is meaningless, because the cos of a negative value is the answer is always positive. Now if you want to try this out in your calc to see if what I'm saying is true, you can actually try it out. So test in your calc. So try typing try typing cos of 60. So when you type cos of 60, you'll actually see that cos of 60 is a half. But also if you put in your calc cos of negative 60, you actually see that the answer remains a half, so it remains positive. So it means when you have the cos of a negative, the answer still remains positive, so it's meaningless. So we can actually ignore that negative sign. So when it comes to cos, we can actually ignore the negative sign. So we end up with something like this, of which you can factorize out the sine 4a. Then when you factorize out the sine 4a from both the numerator and denominator, of course in the denominator we factorize out cos 4a, so we end up with this. So this and this can cancel, and we end up with that, of which sine 4a over cos 4 is tan 4a. Hence we've actually proved it, as simple as that. All right, let's move on to question number 8. So question number 8 is from UNEB 2002, and it was number 12a. So we're being asked to show that this is equal to that. So when someone looks at this from first point of view, you can actually see that this is an example of reverse factor formula. You just look at this, and you can actually see that this is actually reverse factor formula. So we're going to be making use of our knowledge of the reverse factor formula. So let's try to solve this. But before we do that, we're going to actually have to first convert these into a more simpler format using the knowledge of reverse factor formula. So we have that. So let's first deal with them one at a time. So for the sine 3 theta, so this value alone, so for the sine 3 theta, sine 6 theta in reverse factor formula, it becomes that. So we actually have this adding that and then minus that. So when we solve that and simplify, we can actually see that we end up with these values. Now 3 theta minus 6 theta is negative 3 theta, of which, because there is a cos here, we can actually ignore the negative. So this is meaningless. So we can actually ignore that negative sign. So we end up with a value like that. So the reverse factor formula for this other one becomes that. And then we can actually see that there's also a negative sign here, but because this is the cos, we ignore the negative sign. So we end up with the reverse factor formula being that. Alright, so next we have this other value right here, so we're going to work with it. So this is it in reverse factor formula. So 3 theta minus 6 theta becomes negative 3 theta. Now when it comes to sign of a negative, the sign of a negative is actually a negative. So in this case, we're going to pull out the negative sign, and the negative sign will affect this positive sign. So we end up having that. So this negative affects this sign, because this is sign this time. So here the negative actually means something. So we end up having a minus here. So this ends up being the value we get and its expression after the reverse factor formula. Alright, so here also we are going to apply the reverse factor formula. So same thing here, this is theta minus 2 theta, which is negative theta. But because this is sign, we actually are going to consider the negative. So this negative will affect the plus sign, and it will be that. Alright, so all the values we've attained from the reverse factor formula, we're going to place them back. So understand this: whenever you receive values that are already in product form, it is wise to reverse them using reverse factor formula. So you end up with something like this. So now what I see here is I can pull out the a half from the top and also pull out the a half from the denominator. So we end up with something like that. Now when you pull out this a half here, we remain with the negative 1 inside, which multiplies through and it affects these. So you end up with something like that. So these a halves cancel, and then you can actually see from the top that this cos 3 theta and this cancel. Then at the denominator, this sine 3 theta and the plus and the sine 3 theta cancel. So end up with that. Now the half values also cancel, and this is what we remain with. So now that we have something simpler, we now can easily use factor formula to simplify this. So using factor formula for the numerator and denominator, we end up with something like that. But remember that at the top, since we had some part having theta minus 9 theta over 2, which is p minus q over 2, remember that the value we get there is a negative, of which this negative will affect, since it's a negative in a sign, it means we shall consider it. So this negative will multiply this negative sign here, and to change it into a positive. So end up with something like that. Remember, when it comes to sign of a negative, we consider the negative. But when it comes to cos of a negative, we do not consider the negative. So this case, this negative means something, and to multiply the negative there. So this is what we end up with. So this and this cancel, then we remain with that. And then we know that the 2's cancel, but sine 5 theta over cos 5 theta represents tan 5 theta, and hence proved. 9. Alright, so in question number 9, we're being asked to prove that this is equal to that. So we're going to prove from the left hand side. So we have that. So we can actually see that from factor formula. So when we apply the factor formulas, we can actually see that when it's cos of an angle minus cos of a different angle, we have b plus c over 2. So that's why we have that. Then we have b minus c over 2 in that format. So just apply, we're actually applying this formula there. Right, so when it comes to sine, we are also applying factor formula, and we end up with b plus c over 2. So we have 2 sine b plus c over 2 cos b minus c over 2. So that's what we end up with. So when you do that, we can see that this and this cancel, then we remain with that. And then remember, a sine over a cos remains tan. So we have tan b minus c over 2, and hence we've proved. So it's negative tan b minus c over 2, hence we've proved that. So let's move on to question number 10. So question number 10, we actually have this being equal to that. So let's prove from the left hand side. We can actually see that this cos b plus c can be expanded with factor formula to become 2 cos b plus c over 2 cos b minus c over 2. And then 2 cos b, the sine b minus sine c becomes 2 cos b plus c over 2 sine b minus c over 2. So that happens with factor formulas because these are exactly factor formulas. Right, so end up with that, and remember that a cos over sine represents cot. So we have cot b minus c over 2, and hence we've proved that. Alright, so that's it with factor formula. So beyond that, I have some equations for some questions for you in this exercise that I encourage you to try out and practice and get better at your factor formula language. So this is question 1, question 2, question 3. So you've been asked to solve the following equations for values of x 0 to 360 degrees. Then you're being asked to prove the following identities. So you can actually prove this and then get better at your factor formula knowledge. Thank you for watching. Trigonometry. If this video really helped you, feel free to leave a like on the video and feel free to leave a comment to tell me if it was really helpful to you. And then if you're new to this channel, I still remind you to subscribe and then make sure to hit the notification bell so that you get updated every single time I upload a new video. See you all in my next video.